Okay, now that we've gone back and covered the basics of timing and stage delays in IC circuits, let's get into a little bit more complex situations because uh, in reality, chip designers will face a huge number of choices, and you'll sometimes it's difficult to know where to start in even designing a new logic function. Um, some of the questions you might ask is, what's the best circuit topology for a function? You have a lot of different logic gates that you can use, and you can use different combinations for different logic functions. How many stages of logic will give you the least amount of delay? You might initially start out and say, oh, well, if we can do everything in one stage, that will be the fastest. But in reality, that's not the truth, and we'll go into some examples for that. And if you have multiple stages, how wide should your transistors be? You might say the wider the better, the faster they'll be. Again, in reality, that's not always the case. You can wind up using wider transistors in some places, and it'll slow down the stage before it because it's more load on the previous stage. So you need to choose the number of stages, the width of your transistors very carefully. So in the next section, I'll be going through a concept called logical effort. And logical effort is a methodology in order to help you make these decisions. It tries to use a relatively simple model of the delay on a stage-by-stage basis, and allows you to, rather than going into very exact calculations for every single stage, allows you to make simpler back of the envelope calculations that you can do somewhat quickly, but yet still be relatively close to reality in making comparisons between alternatives and getting a good idea. You might not, through these calculations back of the envelope, you might not get the exact delay values, but you'll get a very good idea of what topology will work better than a different topology of circuit. And it does allow you to see symmetries in different logic and be able to make your choices. So let's go into an example and then more details and return to the example. So here's an example of a type of circuit function that you might need to design in the future. We have Ben, who's a memory designer for a motor oil embedded automotive processor. And we're going to help him try and choose the design for a decoder of a register file. So the decoder specifications, we have a 16-word register file. Basically that means we have 16 separate words that we might address, and each word is up to 32 bits. So it means you have to drive one of 16 potential selects to select which of the 16 words you might address, and when you select a given word, you have to drive 32 bits worth of value. So you're going to have 32 bits of load on a given line that you're trying to drive. And each bit represents a load of 32 unit size transistors. So that would be equivalent, a couple foils ago I was saying that the minimum size inverter would be a size 2 PMOS and a size 1 NMOS, so unit size 3. So it's kind of representing, each bit represents having a load of one minimum size transistor or inverter, for example. Coming into the decoder, we have a true and complementary address inputs. So we have 4 bits coming in, it's a bus A sub 3:0, 4 bits coming in, and we have both the A and A bar values coming in. And each input is being driven by a driver external to that decoder that can drive up to a 10 unit size transistors. So keep in mind that's about 3.3 times the size of a minimum size inverter. So Ben needs to decide how many stages are the best to use, how large should each gate be inside of the decoder, and how fast can the decoder operate in terms of unit delays. Again, go back several foils ago or to the previous section where we were saying the unit delay that we're defining is a minimum size inverter with no load on it. So the delay through that type of gate, minimum size inverter with no load, is our unit delay. So these are the things that we're trying to figure out, and we'll go into that in the next several foils. So before we can decide what logic is best and how many stages, etc. we want, the first and foremost most important thing that we have to have a concept of is what is the delay through a given logic gate. So this I would recommend potentially going over this foil several times. Make sure you understand this concept really well. So first of all, we're going to express our delays. We want to express our delays as a process independent type unit. So rather than stating our delays in terms of number of picoseconds or nanoseconds or whatever our given process technology allows us to do, we're going to give our delays in terms of a process independent unit. So our delay D, as we're going to be calculating in all of the upcoming slides, is going to be the concept of the absolute delay, D sub abs, which would be like how many picoseconds or nanoseconds or whatever it is that we're measuring, divided by a process dependent term called tau. And that way we'll get a normalized delay of, this is a delay in terms of number of delay units for a given process. So for example, I said several foils ago that the delay through a minimum size inverter on a given process with no load on it has a delay of 3 RC. So no matter what process technology you're on, the delay through a minimum size inverter with no load is 3 RC. And if we use that as our tau value, we can normalize our delay, and no matter what process technology you're on, you can say it has a delay of a D of 1 is one normalized unit, which is a delay for that process technology of 3 RC, which is whatever the delay is through a minimum sized inverter with no load on it. So just for example, that delay in a 65 nanometer process would be 3 picoseconds, but in a 0.6 micron process or 600 nanometer process, it would be 60 picoseconds. So in both cases, a D of 1 would be a normalized delay of 1 inverter delay on that process with no load on it. But the absolute delay would be very different from one process technology to the other. Again, if we go from one process technology to the other, in both cases we would be talking about a D of 1, but the absolute number would be very different. So that's a key thing to note. So we're going to normalize everything to be process independent. So now that we know that, let's go into the components that make up what a delay through a logic gate would be. So the delay is equal to the value f plus the value p. And I'll go into those. The f value is a delay that is the effort delay. And this is the stage effort, how much it takes to get the delay through a given stage driving another stage. And that stage effort, that effort delay, comes with two components, g and h. The g value is the logical effort for the stage. It measures the ability of a given gate to deliver current to another, whatever its receivers are. So the simplest gate, like an inverter, is defined as having a G of 1 logical effort. It just has a single PMOS, single NMOS. And more complex gates are going to have a higher value of G. So they're going to have a harder time switching depending on what type of load you have. And we'll get into how to calculate the value of G going forward, but just keep in mind an inverter has a G, a basic minimum size inverter has a G of 1 by definition. The value of H is the electrical effort. This has to do with how much load do you have, how many things is this given stage trying to drive. And so this is a ratio of your output capacitance to input capacitance. So the more things you're trying to drive, the more delay it's going to take for this stage to drive out. So this is also called fanout. So if you have like a minimum sized inverter driving 4 other minimum sized inverter, then the C out is going to be 4 times what the C in is, and so the value of H is going to be a value of 4. So we'll get into more detailed and specifics of these going forward as well. And then finally, the value of P, because we have F plus P is the value of your delay. That's your parasitic delay. This is the delay for a gate that's driving no load. So it's the minimum delay that you'll ever have through a given gate. If you don't have any load on it at all, you still have a certain minimum delay. So if we go back to the original definition, D equals F plus P, if we had no load at all, then the F value is going to be G times H. No load at all means C out is 0, so H is 0. So the F value would be 0, and your delay through the gate with no load on it would just be the parasitic delay P. So for a minimum size inverter with no load on it, your delay would just be P, and P for a gate driving no load, by definition for an inverter, is 1, and so your delay for a minimum sized inverter with no load on it is 1. And that goes back to our definition. Since that's the basic unit, we would expect the delay of a minimum sized inverter with no load to have the normalized delay of 1, which is just 3RC. So let's go into some more different types of gates. If you didn't quite understand this, maybe rewind and play through this again. Now that we know the definition of delay, let's look at basically a plot of the normalized delay for an inverter versus a 2-input NAND gate, and the normalized delay as a function of electrical effort. And again, electrical effort is basically fan out, so it's how much load a given gate is trying to drive. So here we have a comparison of an inverter versus a 2-input NAND gate. You can see an inverter with no load, so the very left side of the graph, an inverter with no load, again by definition, has a normalized delay of 1. That's what everything gets normalized against. Whereas a 2-input NAND gate with no load will have twice as much delay, delay of 2, and as you add load, so as you add more things that it's trying to drive, additional inverters on the output, if you have an inverter driving a single inverter, and it would be an electrical effort of 1. Inverter driving 2 additional inverters of the same size would be electrical effort 2. You can see for an inverter, the delay goes from 1 to 2, and when you go up to an electrical effort of 2, it goes from 2 to 3, and it's a linear slope of 1. For the 2-input NAND gate, you can see that the slope is actually slightly higher. So let's go through the values for the parameters of the delay, where the normalized delay again is G times H plus P. So for an inverter, G and P are both equal to 1, and we know that the delay is G times H. So electrical effort is H. So the delay, since G times H, G is 1 and P is 1, the delay is just going to be H plus 1. So whatever our fanout is the value of H, and so our delay is just going to be H plus 1 for an inverter. For a 2-input NAND gate, it turns out the value of G is 4/3, and we'll go into that in future foils. And the value of P starts out at 2, and so the overall delay is going to be 4/3 times H plus 2. So it starts out at a higher value and it has a higher slope. So what would we need for a 2-input NOR gate? So we'll go through the example for why the NAND gate has its values and what a NOR gate value would have in the next foil. So in computing logical effort, first of all we need to know the definition for logical effort. And the definition, logical effort is the ratio of the input capacitance of a given gate for each input to an inverter that would be delivering the same amount of current, so the same equivalent resistance of an inverter. So we need to look at what the input capacitance of the gate is and then divide that by the input capacitance of an inverter delivering the same amount of output current. So if we look at an inverter, the circuit in the lower left of the figure below, you can see your typical inverter, minimum sized inverter, is a size 2 PMOS and a size 1 NMOS. You add the 2 plus the 1 gives us 3, and that's our input capacitance. Divide that by an inverter delivering the same amount of output current. By definition, since this is an inverter, the 3 gets divided by 3, and by definition an inverter has a logical effort of 1. Since it's normalized to itself, it makes sense that an inverter has a normalized value of 1. So G equals 3/3, value of 1. Now if we look at a 2-input NAND gate, which is the center of the 3 circuits below, we can see the NMOS device. We have 2 NMOS in series with each other. Since we want to deliver the same amount of output current as the basic inverter, 2 NMOS in series with each other, if they were both size 1, would have half the amount of output current. So it's like placing two resistors in series with each other. It's going to have twice the resistance. So in order to have the equivalent resistance of an inverter, a NAND gate has to have the NMOS device be twice as wide, so that when you put two of them in series with each other, it has the same equivalent resistance as the inverter. So that's why the NMOS are twice as large, but the PMOS, since they're not in series with each other, each PMOS can drive independently to the output, and there's just a single PMOS between the output and the VDD or VCC, and so the PMOS stays the same size as what an inverter size PMOS would be. So they stay size 2. So when we compute the logical effort for a 2-input NAND gate, each input goes to a size 2 PMOS and a size 2 NMOS. So 2 plus 2 is 4. So our Cin is 4. To normalize it to the inverter, you take the 4 divided by the 3 value, which is our normalized inverter, and you get G equals 4/3. So for a 2-input NAND gate, G equals 4/3. Now when we look at a NOR gate, on the other hand, we now have your NMOS are in parallel with each other, so there's a single NMOS between your output and ground, so they stay the same size as a basic inverter, size 1. Your PMOS devices are now in series with each other, which means they need to double in size so that the equivalent resistance between VDD and your output stays the same as a single PMOS would have been. So you need twice as wide of a PMOS because there's two in series with each other in order to keep the output current drive the same. So our PMOS is now size 4, NMOS size 1. We take the Cin for either input is going to a PMOS of size 4, NMOS of size 1. Add the 4 and 1 together, we get a Cin of 5. Normalize that by dividing by the size 3 inverter normalization, and our logical effort for a 2-input NOR gate is 5/3, so 5/3. So in reality, if you really wanted to get the absolute best value for your logical effort, you would actually do a measurement of your input delay switching to your output delay switching and figure out what the logical effort is by plotting those values versus fanout. But it turns out this type of estimate that we're doing by counting our transistor widths is a good back of the envelope calculation, and so that's what we're going to be going with, something that's relatively easy to do and doesn't require a lot of designer effort and gives us pretty close to the right answer. So close enough for what we're trying to do without taking too much of your time and turning it into a research project on its own. Okay, quiz time. Let's do a quick just test here so that you can test out the information that you've just gotten. We want to figure out what is the logical effort for a NAND 3 and a NOR 3 stage. Since we just went through NAND 2 and NOR 2, let's practice with NAND 3 and NOR 3. So keep in mind, so draw out a NAND 3 stage and a NOR 3 stage. Keep in mind to size it correctly for the same pull up strength as pull down strength in each case. And I'll give you a chance to pause here, and then after you pause, we'll go through the solution. So now hopefully you've gone through, drawn out the NAND 3 and NOR 3, and as I said, we'll go through a solution. So let's start with the NAND 3. So when we draw a NAND 3, we have 3 NMOS devices in series and 3 PMOS devices in parallel for the NAND 3 function. In order to get the appropriate drive strength for the PMOS devices, since those are in parallel, they stay the same size as the base unit inverter, so they're all size 2. The NMOS devices in series, since we have 3 in series with each other, the net drive strength will be 3 times what it used to be. So if we need to, or well, 1/3 of what it used to be, because we have 3 resistances effectively in series with each other, so 3 times the resistance. If we want to bring it down to this, or the resistance down to the same as a unit 1 transistor, we need to make the transistors 3 times as wide so that the net resistance is the same. So we have size 2 PMOS, size 3 NMOS. That adds up for each particular input, A, B, and C. They have a size 5, 2 plus 3, and so the Cn is 5, and the value of G is then normalized, so it's 5/3. Now let's go on to the NOR3. In this case, we have 3 PMOS devices in series with each other, and the NMOS devices are in parallel. So the NMOS device stay their base value of 1. The PMOS device need to be 3 times as wide to be the same net pull-up strength as the initial size 2 device. So 3 times 2 is 6. So each of our PMOS devices is size 6. That means our total Cn is 6 for the PMOS and 1 for the NMOS. That gives us 7. And our normalized value for the logical effort is 7/3. So that gives you an example. Hopefully you did this and can, it all makes sense to you. If it doesn't, again, go back maybe to the previous slide and this slide and make sure you understand this. It is important to be able to go through all of the future information that we'll be going through on logical effort. So now that we've gone through several examples of calculating logical effort, the table below gives basically a more generalized values for the logical effort of several different common gates that you'll encounter depending on the type of logic, inverter, NAND, NOR, tri-state or MUX structures, and XOR, XNOR structures, and it will basically give what the logical effort is depending on the number of inputs, and at least for the NAND, NOR, and tri-state MUX, what the equation is for if you add additional numbers of inputs to the type of gate. So this gives you a relatively easy to understand, and if you want to go and formally prove this or show this to be true, I leave it up to the students to put in a little bit of work and make sure you agree with what's being presented here. On the previous foil, I presented the table that showed the logical effort for a variety of different gates. This one is a table of the parasitic delay, since keep in mind we need the logical effort and the parasitic delay, as well as the fanout, or the amount of load that the given gate is driving, in order to calculate the overall normalized delay for a given logical stage. So down below it gives the parasitic delay for these same common gates, and what it is also as a function of the number of inputs for that type of stage. So if you have in the case of like a tri-state MUX, for example, the logical effort stayed at a value of 2 for every single, no matter how many inputs you had, whereas the parasitic delay for this gate actually goes up quite substantially with each additional number of inputs that you give to this particular type of logic, and that's because you keep adding more and more tri-state mux drivers in parallel with each other, which continues to add more parasitic load to the gate itself. So the gate gets slower with each input as far as its parasitic delay goes, but the amount of additional logical effort doesn't go up. So keep in mind, different gates behave differently. Some, the logical effort goes up per number of inputs. Other ones, the amount of parasitic delay, and in most gates, the amount of parasitic delay goes up with number of inputs, as well as the logical effort going up. So it just depends on the type of logic that you're dealing with. But definitely make sure you understand logical effort and parasitic delay, because we'll be using that in all of our examples going forward. Now let's go through another example. In this case, relatively simple, but we'll be using, instead of just computing the logical effort, trying to compute overall delay. And it'll be simple because it's all the same type of gate. So our example here is a ring oscillator. We basically just have a series of inverters whose output leads back to the input. And if you construct it with an odd number of inverters, it will oscillate and cause a signal that will go from 0 to 1, and cause the next stage to go from 1 to 0, and then the next stage 0 to 1, and oscillate around the circuit. And then if you have an inverting number of stages, odd number of stages, it will continue oscillating around the circuit. So keep in mind, in order to oscillate, you have to go from 0 to 1, go around the circuit, and then it comes back around, goes from 1 to 0, and goes around the circuit. So you have to go around the circuit twice in order to get a full oscillation from 0 to 1, and then back from 1 to 0. So go ahead and calculate your logical effort, electrical effort, parasitic delay, and overall stage delay for each stage, and then calculate your frequency of oscillation. So go ahead and pause here, and I will continue on after you figure it out. So hopefully you've figured it out. Let's go through and determine each of the values here. So our logical effort, G, is 1, 3 over 3 basic inverters. So by definition, G is 1. Electrical effort, that is what the fanout is. So in this particular case, each inverter is just driving one other inverter, so H is 1. Parasitic delay, basic inverter, parasitic delay is 1. So our overall delay is going to be G times H plus P. So that gives us 2. So the delay through each stage is, again, normalized delay to a basic inverter with no load. Our delay is 2 for each stage. And since there's n number of stages, capital N, it takes us 2, basically d times n to get through each stage, or to get through a full ring. And like I said, in order to oscillate, go from 0 to 1 and back 1 to 0, you need to do that 2n times. So we have 2n times d is the amount of delay to get through the ring twice, and then your frequency would be 1 over that delay. So that comes up to a frequency of 1 over 4n normalized delays. So if you had a 31 stage ring oscillator in a 0.6 micron process, if you go back a couple foils for the delay per stage, what 3RC is for a 0.6 micron process, you can calculate what that frequency would be, and it would be approximately 200 megahertz. Let's go through one more relatively simple example and estimate the delay of a fanout 4 inverter. So again, I'll let you try to do this first and then go through it. So go ahead and pause here and figure out the delay, and then we'll continue. So first, let's go through the various different logical effort. So for logical effort, fanout 1, or well, basically an inverter has logical effort of 1 by definition, so G equals 1. Electrical effort, in this case our C out is 4 inverters and C in is 1 inverter, so our electrical effort is H equals 4. Our parasitic delay, again inverter, is 1. So our overall stage delay is G times H plus P. So G times H is 4 plus P is 1. 4 plus 1 is 5. Our stage delay is going to be a delay of 5. And again, this is a normalized delay depending on process. So if we, depending on what process we're using, we can calculate what the absolute delay would be. So just as an example, going back to the 0.6 micron process that we had mentioned earlier, the kind of unit delay of a single inverter stage is 60 picoseconds, so 5 times that would be 300 picoseconds stage delay in the 0.6 micron process. In the 65 nanometer process, where it was 3 picoseconds, the 3 times 5 would be 15 picoseconds in a 65 nanometer process. So that tells you how you can do your calculations in a process independent manner and then eventually convert to the process that you're on. So this is an example of how that comes in useful, where you don't need to know what process you're on in order to calculate delay relative of one type of gate or one type of stage relative to another. We don't necessarily need to know the absolute delay while we're trying to optimize our logic function.